We have Sagnik Mukhopadhyay as a speaker. Sagnik is an associate prof at the University of Birmingham, and his primary interest is algorithms and complex. Prior to joining Birmingham, he was a lecturer at the University of Sheffield, and before that, he did postdocs at Copenhagen, KTH, and IIUK Charles University. And before that, he did PhD from TIFR with Arkadir Chattopadhyay, where he was awarded the TCS PhD fellowship. With this, I hand it over to Sagnik. So, we'll be talking about distributed computing, and he'll be giving a primer on distributed computing. So, yeah, I'll explain this. Okay, right. Did you give me mine?
Thanks. Yeah, this is essentially going to be a classroom talk. So I think it's only for that now. Okay, let me see. Hello. Yeah, it is on. It is on.
And that is a bit different, I guess. Okay. The general wire mic is different. Sure. All right.
All right. So this is going to supposed to be interactive. So I have till 5 o'clock. So I have something planned, and let's see how much I can go over it. But if any point in time, if you have any questions, please do stop me. Yeah. Right. So we are going to talk about graph problems over networks, and there are many ways you can study these problems, and many computational like paradigms in which you can study these problems. For today, I'm just going to pick one, and we are going to work on that. And that is called CONGEST model. I will come to it, but let me give you a brief idea about how we think about graph problems in the distributed setting. So there are, when we talk about distributed setting, we classify the graph problems roughly in two categories. One is called local problem, one is called global problem. So it's essentially local means that once you have a problem over the network, and every node is a machine, a processor, and its output of the function depends only on a small neighborhood of it, right? That's a local problem. Think of like, maximal independent set. Yeah. So for a vertex to check whether it's an independent set or it's in the independent set or not, it just need to check its neighbors. Whereas the global problem, the output will depend on the whole of the graph. It's a property of the network. So for example, so let's see, in the local, you have, let's say, graph coloring maybe, and maximal independent set, some sort of network decomposition. Is this visible? First of all, this is visible, right? And for the global, you have maybe I will use a different color then. Let me use green then. So the global problem would be something like, spanning tree or connectivity or minimum spanning tree, or more classical would be min cut, max flow, this kind of problems. Well, to understand whether a set of edges is a min cut, you really need to know about the whole graph essentially. And what we are going to focus on today is essentially one of the global problems, and specifically the minimum spanning tree problem. Okay. It's an independent. The maximality, it's not maximum. You need to check the maximality. And that is important, but because maximum independent set is not a local problem, because it's related to vertex cover, which relates to matching, which relates to min cut, and so on and so forth. Yeah. So network decomposition would be something like, low diameter decomposition, let's say. So you want to, the classical way of doing it would be you have a graph, you decompose it into a bunch of clusters. They're all connected and heavily connected, but the edges that is in intercluster edges, you sort of cut it down by a constant factor, and you keep on doing it. That's how people usually treat network decomposition. One of these ways to do it is expanders. But anyway, so, this network decomposition is essentially one of the, it's not a specific problem. It's, you need to talk about on which parameter you are decomposing the network. Right, so the model that we are going to talk about today is called CONGEST model. And the way it is defined is the following. So you are given a graph. Let's say this is a vertex set, this is the edge set, and essentially always we are going to use n to denote the size of the vertex set, m to denote the size of the edge set. And this graph is going to be both the input of the graph problem and the communication network. What do I mean by that? So let's say you have this graph. So every vertex, so this is a vertex, it will know a few things. So it will know the value of n, the number of vertices in it, in the whole graph. It will also know the ID of itself, and it will also know the incident edges. So we will know this guy, and this guy. And that's all its input. And based on that, computation happens. And the computation happens in a synchronous round. The best way to think about it is like a night and day. So during the daytime, every vertex communicates. So they will send messages. So we will be able to send message to each of its neighbor. And in the night, they will do local computation. So at night, they will take stock of whatever they have received and whatever they have sent. And based on that, they will do some local computation, and this will repeat. And the CONGEST specifically has one more restriction. It's called channel capacity. And this is a crucial restriction, which makes CONGEST more amenable towards real-life network. There is a channel capacity of B, and usually this is order log n bits. Okay? Which means on a day, every vertex can only send order log n bits to one of its neighbor. But it has every freedom to send different messages to each of its neighbors. Okay? And the measure of complexity is the number of days, essentially the number of rounds. This is the traditional measure of complexity. Nowadays, there is also work on the total communication over the whole network. Okay, and the good thing about talking about this area is that you will see that the current research focus is very close to what I'm saying. So, for example, this has been looked at for a while. This is pretty new. So there's already a bunch of open questions over here. Right, so this is new. And now, what we're going to do today. So today, the plan is the following. So I'm going to talk about minimum spanning tree over CONGEST. So when I'm talking about minimum spanning tree, I'm only going, primarily going to talk about algorithms. And from there, I will talk about something more general, something called part-wise aggregation. This is a general framework in way distributed computation or CONGEST works. And I'm going to talk about something called low congestion shortcut. So this is a very new way of characterizing distributed computation. Yeah. This is mostly upper bounds. For the lower bounds, what I have planned is I'm going to talk a little bit about how to prove unconditional lower bound for CONGEST, mostly distributed verification or approximation even. And I'm going to talk a little bit about universal optimality. Now, let me give you some citations for these things. So the oldest thing I'm going to talk about is this work. So this is by Kutan and Peleg, and this is a work from 98. Part-wise aggregation and low congestion shortcut is pretty new, and I mean, each of these papers that I'm citing, these are the first paper. So after that, a lot of work has happened. But this is a good starting point. This is a paper of Ghaffari and Hopler in Soda 16. This for the lower bound side, I'm going to talk about a paper which appeared in Stock 11, and for universal optimality, I'm going to talk about Hofler and company, which is a paper in Stock 21. So you see, these are very recent work. Yeah. Right. Now, let's talk about how distributed computation works. So essentially what happens is, like, if you look at any typical distributed congest algorithms, what happens is, like, you have this graph. The way it works is like you break it up into chunks or subgraphs. Sometimes they're connected, sometimes they're not connected, but usually they're connected. What you do is, like, you aggregate information inside clusters. Once you have this information aggregated, let's say there is a leader in every cluster who has all the information, all the necessary informations. And once you have that, you have to route it to other clusters, right? And so let's say this guy has aggregated something over some spanning tree on it. So you sort of aggregate it, and this guy has the information. Also, this guy has the information. So you have to route to this guy some amount of, so that they can do combined computation. But it's not just only this guy is routing to this guy. It has to happen over all possible combinations of clusters. So you have to coordinate them. And this has to happen simultaneously. So there is a flavor of parallelism there, and which is not pretty far away. There is a way you can actually formalize it. You can come up with a meta framework where, if you design an algorithm, it will give you both a PRAM algorithm, which is a parallel algorithm, and a congest algorithm in a black box way. This is, again, a very recent work. I think it's a last year's work. Okay, but the flavor is there, and you can formalize it. But we are not going to go over there. We're going to talk about something more basic. It's no, there is no central authority over here. So
differences here. So, what do you get in those models compared to, let's say, PRAM or?
So MPC is extremely powerful. So this model, the congest, is not that powerful. MPC gives you a very specific way in which the machines can talk to each other. So let me take a little bit of digress over here. So what happens is, like, in the MPC, there are MapReduce, essentially, that's the model over here. There are a couple of phases, or a few phases. Once, what happens, you have a bunch of machines, and let's say each machine is a point in this set, right? the input is going to be distributed amongst those machines. And usually you look at the regime where the local memory is not too big. Yeah. So let's say if you have an n-bit input and you have like t machines, then like every machine will have n over t, and you are going to look at t is something like Pauline n, like n to the epsilon or something. Yeah. Now machines get these inputs, and in the next round, what they can do is they can have a way to talk to each other. And this is a phase called shuffle phase. And this is a very well-structured phase. You cannot just arbitrarily talk to anybody. There is a mapping over there by which you are going to talk. Once you have the shuffle phase, you do local computation and keep on doing shuffling. And at the end of the day, you give the answer. Now, this MPC is almost as powerful as circuits. And proving a circuit lower bound is one of the outstanding open questions in the circuit complexity. So there are papers by Andrew Drucker and all, and also a Tim Ravgarden's paper where he shows that this model, if you can show something a round complexity, which is, let's say, constant round complexity, then that will give, if you show some lower bound of super constant, then that will show a super constant lower bound for circuits, which is an outstanding open question. So MPCs usually round complexity is going to be much, much, much smaller than CONGEST. Yeah. But this whole MPC cluster needs to be with somebody. Let's say Google has an MPC cluster. Whereas this model, these nodes you can think of like machines in the internet. So it's not really a structured network. Is that a reasonable answer? Okay, good. Now, for any problem, let me talk about some trivial bounds. Can you give me, can you think of a trivial lower bound for an interesting problem, for any interesting problem in such a graph? I mean, of course, the lower bound has to be with some parameters of the graph, but what will be a parameter which immediately lower bounds this? Any idea? Great. So omega d is pretty obvious because, and this is where the globalness of the problem comes in picture. This guy, if he has to send some information to this guy, it has to travel through a path, which is the longest path in the network. So it's omega d is obviously a lower bound. If you think a little bit, also an upper bound would be order m. M is the number of edges because every vertex just can flood the network. Yeah. And usually the regime that we are going to look at, it's going to be D is going to be something really small, polylogarithmic or n to the power order 1. Think of like a really small number. Yeah, so the network is very well connected. But then there is a huge gap over here. And we want to address this gap. Is that okay? So far? So now let me talk about having this. What can I do about minimum spanning tree? So right, everybody knows at least one algorithm of how to compute a minimum spanning tree, right? What would be the algorithm? I guess you guys know Prim's algorithm. You guys know Kruskal's algorithm. Is there any other algorithm you know of? Good. Yeah. So the point about why people like Borufka is that it's a very parallel algorithm, but it's also a very intuitive algorithm as well. So let me just give you a brief idea about how Borufka works. You start with your spanning tree to be empty, of course, as you do. That's the initialization phase. And then you repeat the following. So at the very beginning, think of every vertex as a connected component, and we are going to grow this connected component, right? So each connected component adds its cheapest outgoing edge to T. And that's it. That's the algorithm. You just, I mean, you terminate when the whole thing is connected, right? Now, let me make a claim, and this is an obvious claim, that if I have to simulate this algorithm in CONGEST, what would be the runtime, or what would the round complexity of it? Of course, it will be the number of iterations of this loop times the number of rounds per iteration. Right? There is no claim over here. Essentially, this is just an observation, right? Now, something we can get a handle of right now. What would be the number of iterations over here? Any guess? Not your in them, because you know this algorithm. At this point, I'm just wanting you to guess. You don't have to be the correct answer. Order n. Why so? Of course, order n is the right answer, but I want a more precise answer. It's much smaller than order n. And because it's a parallel kind of algorithm. So what is happening? So why it is different from Kruskal, for example? Kruskal sort of, or Prims, let's say, it sort of deals with many clusters at the same time. Now, if you start with, let's say, at any iteration, k clusters, yeah, can you give me a bound on the next round? How many clusters will be there, maximum? Every cluster chooses one of the edges that is going out, and that edge can connect to another cluster. So every cluster will find a pair of it and will merge. So what would be the worst kind of merging possible? Exactly, right? So that would be just a matching, right? So this guy gets an edge and it merges to this guy. This guy gets an edge, merges to this guy. This is the worst possible. The best possible would be, there is one guy and everybody finds an edge to that guy, right? The star topology would be the best possible. And this will give you, it will cut down the number of clusters by half. How many times it can go? Log n many times. So this is order log n. So we need to talk about this. Right. Now, let's talk about one iteration. Let me use that area. Right, so yeah, we are doing a congest algorithm, right? One of the things we talked about is like what we have to do in each iteration. Let me write it down. What do I mean by number of rounds per iteration? Let's talk about one single iteration. What am I doing in this iteration? I have this bunch of clusters. It says C1, C2, C3, dot, 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 C capital N. And for each cluster, I need to find an outgoing edge, which is the cheapest. That needs some communication and some computation in the distributed network, right? Because there are a bunch of vertices over here. They need to agree on what is the cheapest outgoing edge. And that's what I mean by the number of rounds needed to do that, right? Is that clear? So we need to find the cheapest outgoing edge for every cluster. Let's talk about some trivial bounds again. If you have a cluster, just focus on one cluster, right? How many rounds do you think it will take to find the minimum outgoing edge? Order of degree. Why do you think so? Well, I mean, what will be the algorithm? Yeah, but let's say this cluster something like this, like it's a path essentially, right? So then this guy will say that this is my cheapest outgoing edge, but then it might not be the cheapest. It has to tell this guy, oh, my outgoing edge is this much, but this guy said, no, I have a cheaper one, right? And it keeps on going. So that sort of gives you the answer. What would be the, so number of nodes in the cluster. Can we come up with a better upper bound? Note that its communication is not restricted to this cluster. It can talk, it can use the whole graph to communicate. If I give you the whole graph, can you get this number down? But I'm anyway going to write down your bound first. So let's call that order of, it's essentially, let me try to refine what you said just a little bit. Let's say I'm going to call it DCI, which is the diameter of the cluster. Right? Yeah. Yeah.
Steepest edges.
Yeah.
Then steepest outgoing edges.
Yeah.
Okay, so one question, like, does the node know like what all are there in its cluster? What all nodes are there in its cluster?
It doesn't, but can you address that as well? Everybody knows that I am in the cluster, I am in which cluster, right? Let's just assume that everybody knows which cluster that particular vertex is in. So let's say I'm a vertex, I know I'm in the cluster 10. I'm going to look at my neighbors. I'm going to ask everybody, report me your cluster. And people will report. And now I know which of my neighbors are outside cluster. That's just one round. I don't care about that. So let's just assume that I know everybody who is in the cluster and who is not in the cluster. So I can immediately find the edges that is incident on me, what is the cheapest one. That can be done with, you need one more round, right? We're talking in asymptotes. We don't care. Having said that, do you see an algorithm that you can aggregate this information in diameter of the cluster round? Why? Essentially, think of it as a BFS inside the cluster, and you start from the leaf node and you sort of start aggregating it. Two vertices send that this is my cheapest, this is my cheapest. It comes to this guy and it will say, oh, I got this guy's cheapest, this guy's cheapest, here's my cheapest, what is the cheaper amongst all of them, right? So you can do it. And if you sort of like climb through the BFS tree and you have D of CI for every one of them, right? Is that clear? Communicate first. Well, you first have to create this BFS, right? So everybody knows that who is my parent. You don't really need to know when. So you can just flood every round. Like every round, you can just flash that this is my cheapest, this is my cheapest, this is my cheapest. And whenever it's important, it's getting used, right? But good question. D of CI is an immediate upper bound on it. And no, they don't know D of CI. First, you create a BFS and then you just press it. Yeah.
They don't know you have created.
No.
And okay, they know that there is some node some minimum value is there, but whether it's minimum or not, that is only clear if they know DCI.
Yeah.
Otherwise, it's not clear to them.
No, so there will be one leader who is a root of the BFS, and he or she will know that what is the minimum, and all the other guys, they don't have any idea essentially. Right, so you sort of aggregate, and then you can like converge cluster again.
You're saying already, I have already aggregated information from all the nodes in my cluster, like D. So I don't know DCI round. How do I know that okay, it's kind of done already?
So you mean like I think that's the same question that he asked. Like, what will be the time by which I will know this, right? Like when the root will be sure that I now have all the informations, right? So that. Yeah.
How do I know that?
Think a bit. So it's I think best way to think about it is the day night. How many days? So you you communicate at the day and you compute at the night.
But you said that they will.
So every day they will kick.
But
I mean, irrespective of what is happening, you just keep flashing. One of the ways you can deal with it is like, you know, the size of the cluster. So whenever you are aggregating the information, you also aggregate the information amongst how many nodes. Well, you will see that it's not very hard to actually also every node to know the size of the cluster.
My neighbors who are in my cluster, but
Yeah.
if I need to know all the number of nodes who are in my cluster, then I have to communicate to all of the nodes, and then only I'll get to know who are in my cluster.
Yeah, but that's just one round, right? I'm not charging the total communication. Diameter. The degree of the graph. The diameter of the graph is the maximum distance between two nodes in the graph. That is the distance. There is no minimum distance. That's the definition of distance. Yeah. That's the diameter. Yeah. So when you talk about distance, is the shortest distance is the metric. So go with that. CI would be connected. So you can get a tree out of it. Sure. It can be really large. It can be n. I mean, for example, here, you can have n over 2 nodes over here, and that can be really large.
yeah, been bounded by the depth of the tree, like depth of the cluster.
The depth of the cluster itself can be order n. Yeah, sure. I mean, you can do it. I mean, this d of ci, the diameter, is essentially the depth of the tree, right? Or twice a half of the whatever. I mean, you have to go up and down, right? No. You create the BFS tree, right? So as a node, I will send my tokens, right? Yeah. These are the nuances I might forget, but thanks for reminding. Yeah.
Models initially take some time to understand.
No, that's it.
Initially, I was thinking for each communication about one edge, it's one round, but now I understand no. Actually, you can count in the same round, you can talk to multiple nodes, but within one edge, you can only have order log n.
That's correct. That is correct. So this is one of the obvious things that you can do. My claim is that in a cluster, You can also do this using the global BFS tree as well. Yeah. So you can do it in order D for one cluster. Do you see why? Instead of using their own BFS tree, they can just use the global BFS tree as a way to communicate. Yeah. What is the qualitative difference between these two? What might go wrong? And this is where the channel capacity comes in play. When I'm doing this, yeah, the local BFS tree is the cluster's own BFS tree. Only the cluster uses it, right? Whereas if I use the global BFS tree, every cluster has to use it. So now an edge in this global BFS tree will have informations coming from many clusters, and they have to keep them separate, right? But you only can send log n bits of information in a channel in a round. This is called a congestion. You create a congestion over the net, over an edge, right? So order DCI. So the DCI, as I've written, is at least going to be D, because D is the shortest, and it's at most N. So one strategy can be based on your connected component size. I want to, of course, order N, you can do it, it's not a big deal, but I want to get it down even less. I want the number of rounds to be sublinear. So let's talk about two parts. So based on the connected component size, if it is a small connected component, and I'm going to define what is small a bit later, I can do this aggregation inside the cluster. If it is large, I'm going to use the global BFS tree to communicate, right? That would be one of the straightforward way of dealing with this. And this is the kind of trade-off you will keep on seeing everywhere, right? Right. So let me go to that part and let me try to formalize this. So what do I mean by a small connected component? So this means the size of the connected components is at most, let's say, square root n. And this is the right trade-off we will see. If it is square root n, I know that the diameter of the component or the cluster is also bounded by square root n, right? So small clusters can come up with this within square root n rounds. Yeah, you're right. This might not be the correct thing. Yeah, you're right. It might just have small number of things. You're right. So for small, I want to aggregate inside. For large, string, so this means the size is at least square root n. I want to use the global BFS tree. Now, how many such large clusters can be there? Exactly. Number of large cluster is at most square root n. For each cluster in the BFS tree, how many bits are you sending through an edge? Think about one cluster and the global BFS tree. You are just aggregating, right? You are just it comes to a node, it will check who is the minimum amongst all of them, and it will send across that minimum. Maybe some more additional information ancilla, but it comes down to order log n, right? So order log n per cluster, there are square root n such clusters. So each edge will be used to send across square root log n bits of information. Let's not worry about log n at this point. Let's just say this is square root n bits of information. Okay. Now, So let me try to write it down. Maximum number of aggregation operation and edge E participate in is square root n plus 1. I will say this plus 1 is not really important, but this plus 1 is coming because let's say you are using an edge from a global BFS tree. It is not part of any of those clusters, but it's a part of one of the clusters, which is a small cluster, right? So that small cluster might have used that edge as well. So that will require one more bits of information for flowing through. So this part is because of the large CC, and this is because of the small CC, but let's not worry about the plus 1 for now. So this is, as I said, this is called the congestion on E. No, I'm just talking about one iteration. Correct. Correct. Now, also, what is the maximum distance a message has to travel? That's something like order D, right? Because you're using the global span tree, right? So this is called the dilation of the network. Now, I'm going to say something which is this is where things become a little bit interesting about how to route information. This is the part where the routing becomes a little non-trivial. So this is the part you might have to pay attention a bit. Let's say, assume that I'm just going to give some names on it. So congestion is something like gamma, and dilation is, let's say, delta. Now, this is the situation you are in. You have to send these messages across, and the congestion that you have over every edge, that means that the gamma many messages can travel to one of the edges, and each message has to travel maybe the delta amount, right? How can I what would be the optimal way to schedule this routing of messages? Yeah. Now, why this is an important question? You can think of like you are sending these messages, you start at the same time, right? And some edge of the BFS tree may be used 10 rounds down the line by cluster 1 and 20 rounds down the line by cluster 2. That's fine then. Even though this edge is getting used multiple times, they are using in different times. So you are not having any congestion. But things might be not that simple. So you can easily cook up a counterexample where the messages are coming and every time one edge is getting congested, you sort of like a pipeline through it, again, another edge is getting congested. And it's quite a interesting thing actually to come up with a counterexample of, an example where this is actually happening. You can come up with this. How do you solve this? Exactly. So this is a theorem. If you haven't seen before, maybe you can use it as well. So this is a theorem that is from 94. And the theorem states, that maybe I will use the red. You can route this information in order gamma plus delta rounds. That's it. Okay, not gamma times delta. That would have been the problem. Every time you are taking gamma and then again, next step, another gamma and so on and so forth, but gamma plus delta. Any idea how to come up with this? It's a very simple process, but it uses randomization. If you haven't seen before, it's a bit hard to come up with this. Essentially, what you do is like you send every message, use a random delay between 0 and gamma. What do I mean by this? You do not start simultaneously. Everybody tosses a coin, picks a number between 0 and gamma, and starts a message on that round. And then it goes normally. Now, why it works? So if I start with this, what is the expected amount of congestion on E? It's supposed to have gamma amount of congestion, right? But you gave this random delay. So look at all the messages that are supposed to congest that network. They start in very different time. So on expectation, the number of messages passing is order 1, constant many messages. And then you can also do it like order log n with high probability. If you just throw in an extra log n factor, then you can do concentration bound. There are only m many edges, which is n square. So Chernoff works out and so on and so forth. These are like standard tricks you can do. All it's saying is that there are only log n many messages going through, but this is something that I can handle on every edge. So there is no congestion over here. So you can just use the random delay, which will give you the gamma and then delta. Is that clear? You don't have to understand the proof so far, but this is a very powerful method, and this will be using. This is used like dotted across the literature. They all use it. Cool. Now, so yeah, essentially, if you are a cluster, you know that you're only going to send one message, right? Think of a cluster as they're now a super vertex. So the super vertex sort of chooses a delay, 3. So all of vertices of the super vertex will start their computation on the 3rd round. Yeah, and so on and so on. Now, there are also nuances here, like how will the vertices will agree on the random delay, because there are many vertices. You can think of like there is a leader who chooses the random delay and then percolates it down. Something like that. These are just a broad stroke techniques. If you have to implement it, you have to be a bit more cautious, right? Or you can do something even fancier. You can look at some pairwise independent hash function and use that to get the random delay. Those tricks are used. Yeah, but this is the broad stroke algorithm. Now, if you have this, do you see that now I can do this MST in square root n rounds? So that's the main claim, right? So small clusters, you just inside, you do the aggregation, square root n rounds, you're done. Big clusters, use the BFS tree. The maximum congestion is square root n, and the dilation is d, because you only have to send. So you get square root n plus d. And so you get the theorem, which is the Cotten-Pelex theorem, which says that MST can be computed in order tilde square root n plus d rounds. Good. At least one of the algorithms you have seen. That's already interesting. I'm going to talk a little bit about the partwise aggregation, and then maybe we can take a break. Right? Is that okay? Right. That's exactly what I'm coming to right now. Okay. I mean, you are in for a treat now, because the square root n plus d is essentially the gold standard of distributed computing. Good. Let's see how much I can talk about. So what we are doing essentially is we are doing some sort of part-wise aggregation. Aggregation can be many things. What we are aggregating now is the minimum amongst a bunch of numbers. But you can also aggregate, let's say, summation, something, or maximum, or whatever, you know, any aggregate function. And part-wise aggregation is, again, you have this graph and you have these clusters that you already have computed. You want to aggregate something over here and then want to route this across, right? And this might seem like the template for MST that we have seen. But as you said, this is much more general. Any divide and conquer algorithm that you can think of will use something like this. When you divide the graph, compute, and when you conquer, you have to route, right? So let me try to define something. Let me try to define something called a shortcut. So what do we have? A shortcut we will call shortcut with congestion gamma and dilation delta for a partition of the vertex set into C1, let's say C capital N. So this is something I'm going to define. So you're given a partition of the vertex set. Again, these are your vertex set partition, C1, C2, Cn. And I'm going to define something called a shortcut with this congestion and this dilation. This is essentially going to be set of subgraphs H1 to Hn. These are all the subgraphs of your original graph G, such that two things happen. One, for all I, the diameter of the G of the cluster plus Hi is bounded by delta. And second, for all edge, the number of I such that edge participates in this G of Ci plus Hi is going to be bounded by gamma. So there are a lot of maths over here, but all I'm saying is very simple, right? You have the clusters, you have a bunch of parts. For each part, I will come up with a subgraph. Maybe not, it has nothing to do with whether it's in the cluster, outside the cluster. It's just a subgraph of the graph. For cluster C1, I have an H1. The property is that when I add this subgraph to my cluster, the diameter reduces. That means this to delta. But I also, these subgraphs do not overlap too much. So an edge can only participate in gamma many Ci plus Hi's, right? This is called a low congestion shortcut because low congestion because of this, right? Now you can see that this is sort of like falls out of your MST algorithm. What was your, okay, so let me say that first observation. Let me make some observations over here. Observation, if you have such a shortcut, low congestion shortcut, then part-wise aggregation can be solved in do we agree on this? Right? This has a name, this quantity. This is called shortcut quality of the graph based on the partition, or the way I have defined it. So P is the partition. Okay, so let me just say this is the partition. Okay. And this, when I say partwise aggregation, I'm meaning it is partwise aggregation with respect to this partition. Just easy to see.
Like expanded decomposition, we have the property this diameter is kind of small.
You get it for free.
Yeah, but here we have to find some kind of expanded length thing, but we just do this cluster. We add it and then it becomes like a expanded.
Absolutely. Yeah. But the point is that when you do the expanded decomposition, it sort of gives you some kind of decomposition, but this is worst case. The partition is given to you, right? It's the other way around. And because I've defined shortcut quality of the graph G with respect to a partition, let me just define shortcut quality of the graph itself by maximizing over the all kinds of partitions. Yeah, so it's just like definition. Nothing much is happening. Right. Now, let's see if I can get some trivial bounds on shortcut quality of G. Okay, so I have to talk about the congestion. I have to talk about the dilation. It's a sort of like a free form definition. All you have over here is a partition of the vertices. And inside every partition, you are computing an aggregate function. It can be any aggregate function. For what I care, max, plus, parity, whatever you can think of, right? Matrix multiplication will not be an aggregate function because it really depends on which order you map it, right? Yeah, that kind of things. So let's talk about congestion, dilation, and the shortcut quality is going to be congestion plus dilation. So given any partition, can you come up with a shortcut of some quality? What would be a basic shortcut? Let me give you some more pointers. Let's say I do not put any HIs. Their HIs are all empty. No extra edges are added. What will be the congestion? You are working in a cluster. You are aggregating inside a cluster, right? Which means it's an aggregate function, which means that every edge is only going to get used once. So congestion is 1. Extremely nice. But what is the dilation? It can be as big as n, because the part itself can be really thin and long, right? So it's easy to come up with a shortcut quality of order n, right? Obviously. So this is like HIs are empty. Good, I love it. Now, can you come up with another extreme of it? What would be the other extreme? When you have used it already, use the whole graph. All HIs are everything. What is the dilation then? D, right? You can use the BFS tree of the graph. What will be the congestion? Can be at most n, right? Because there can be n parts of the graph. Again, it's becoming order n. D is much smaller. D is bounded by n, so it's order n. Now, we'll also say you can also get, this is the part which is, you can sort of get it from there. You can get square root n and square root n plus d. Right? This is what we have solved so far. Given any part, you just look at the smalls and the large. Small, so you're just going to do, HIs is going to be empty. For the large, you are going to give it more. right? So it becomes square root n plus t. So you have a square root, the shortcut quality of course, square root n plus t. And MST is essentially is a partwise aggregation function. So all I've said, I'll just formalize the whole thing. MST can be done in shortcut quality, and shortcut quality is at most order square root n plus t. Good. Now, coming back from the break, what I'm going to do is the following. It's a maximum across partition. It's the worst case, worst possible shortcuts that you can get. Right. I'm saying the worst possible itself is bounded by square root n plus t. But that's for what if I give you a graph, that might not be the worst possible thing, right? It might have its own quality of shortcut, which might be much better. So this algorithm, what I said is not only give you a square root n plus t, but for any graph, it will give you an algorithm which is of which has the round complexity, which is of shortcut quality, right? Now, is there any graphs, any class of graph for which we can theoretically guarantee that there is a better shortcut? Yeah. For example, is there any graph for which we can say that there will always be a shortcut of quality D? That would be the amazing, nice result, right? If it can capture a large class of graphs. Now, coming back from the break, we'll see two things. One is that yes, there is a class, and it's a pretty large class called planar graphs, which indeed has order D quality shortcut. So you can solve MST on planar graphs in order D round. Second, we will also see a lower bound of square root n plus t. But the square root n plus t is again the worst case lower bound. This is called an existential optimality. And that's what we're going to see. But last year's paper, if you look at it, they will show you that you can actually have universal optimality in the sense that you can prove a lower bound of omega shortcut quality. MST needs omega shortcut quality. It completely characterizes. Okay, and these are the two things we will see. Let's take a break, and if you have any questions in the meantime, I'm happy to answer.